back. All right, so yesterday we started in section 1, 2 about just all different types of functions, right? We talked about how we could model different real-life situations with certain functions. We talked about mathematical models. We talked about empirical models as well. And remember, empirical models, how they differ from mathematical models is that we're using more data-driven stuff to create our equations, to create the things that we're going to use to predict what's going to happen in the future. And then we did a linear regression, right? That's your lin reg in your calculators. So we do a linear regression. But we could also have other types of regression as well. A ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground, and its height h above the ground is recorded at 1 second intervals in Table 2. Find a model to fit the data and use the model to predict the time at which the ball hits the ground. Now, those of you taking physics, or those of you that have taken physics, you might know that any falling object or any thrown object follows the path of a parabola, right? So any falling object, like this ball that's dropped from the CN Tower, any falling object is actually going to be a quadratic, right? Any thrown, any projectile motion is in the form of a parabola. So we can assume that this is going to come out quadratic. Now, we're going to see that within the statistics as well, though. So what I'm going to do here first is go in and I'm going to stat, edit, and I'm going to clear out my lists and plug in my new stuff. So if you want to do this with me, by all means, do it. If you're like, I remember this stuff, we did this a million times in Algebra 2, I don't need to do that again, that's fine too. So I've got all my data plugged in. It's 0 to 9, and then I've got height in meters. Now remember, the best course of action from here is to create your equation. So go back out to your home screen and stat calc a quadratic regression. Stat, scroll right once to calc, and then choice 5 is the quadratic regression. Now, your calculators, some of you guys' calculators look a little different from mine. Mine goes to this screen when I do this. Some of you guys, you have to scroll down to hit calculate to do that as well. That does not look like a good fit, though. I'm going to go back into edit and make sure that I didn't. Oh, look. See, do you guys see what I did there? I said, this does not look like a good fit. A 0.4, I might have done something wrong. So I went back into stat edit and look at my second data entry. 1, 45. No, 1, 445. I apparently got a little too quick. 431, 375, 332, 279. Okay, that looks a little bit better. I'm going to go run that again. Second entry is going to get us our exact same last program run. There we go. Much better R-squared value. Remember, the R-squared value is going to tell you how good that fits, right? If you don't have the R-squared value, you turn on your diagnostic. You hit second catalog, and that's every function in your calculator. And then you can either scroll down to D or hit the D alpha button. It's the matrix button, the X to the -1 button. And scroll down to hit diagnostic on. We did this like a million times in Algebra 2. Hit enter, and then it says done. And now when you run your quadratic regression again, the R-squared value should be there. So we've got this quadratic here. Let me pull this over. And then it says, so my quadratic is y is equal to negative 4.9 x squared plus 0.962x plus 449.36. I don't know how I did 1 to 1 decimal place. I did 1 to 3 decimal places. 1 to 2 decimal places. I'm out there. So here's my equation. This is the equation that models the path of the ball. Right? This is the equation that models the path of the ball. This is really interesting here. You guys know this value, negative 4.9? You guys know that? Isn't that the half of acceleration due to gravity? Negative 9.8, right, meters per second squared. But that's half of that 9.8. So that's an important number there. But this is just what. This is our equation that models this path. Now remember that we could go into our y equals, and I'm going to clear out my other stuff here. Keep your plot 1 on. But now if I want to put in my equation, my regression equation, this is how we do it. Bars, choice 5 is statistics. Scroll right twice to EQ. And there's our new regression equation. And now I'm going to hit zoom stat and see how it traces. And there we have it. Okay, so this is the path of our ball. Looks like it's got some sort of acceleration to it. Not necessarily drop, but. And now what we're going to do is find a model to fit the data done and predict the time at which the ball is going to hit the ground. We're going to figure out how many seconds the ball is going to take to hit the ground. Now, think about this logically. If I wanted to do this algebraically, if I did not have my calculator, if I wanted to do this algebraically, I would need to go in and solve this equation for 0. Like I would need to go in here and say, okay, get that to go away, and say equals 0. And the best way to do this would be to run the quadratic formula, where A is negative 4.9, B is 0.962, and C is 449.36. But we have our calculator, so let's use them. Second, calculate 0, because that's what we're really finding, right? We're figuring out when the x value is going to have height of 0. So 2. And now remember that for zeros, you have to choose a left bound, a right bound, and then a guess. So I have to trace all the way over until I'm going to hit my 0. And the calculator on my screen is a little bit laggy. Okay, I'm going to hit it right here. I'm going to keep going to the right. See my cursor's like down there now. What I'm really looking at is my y value. I wanted it to go negative so that I knew it was below the axis. And then I'm going to hit enter somewhere in between. Okay, there it is. The x value, come on. The x value of 9.67 has the y value of 0. 9.67. So what is that telling us? It's going to happen at 9.67 seconds. If I were to run the quadratic formula, I would get the exact same number. Actually, that's a little bit more precise because I had to round, right? When I made that equation, I had to round. And I rounded really weirdly, right? But I had to round. So this, I'm not rounding at all, which is really nice. And when you do it in your calculator, it's unrounded. So we've done linear regression. We've done quadratic regression. Right? We've talked about linear models, quadratic models. But there's all other sorts of functions that we can have as well. So I'm going to run through some of them. For example, a power function, where we have x to the power of some number, like x squared, x to the third, x to the fourth, x to the whatever. X to the, where n is a positive integer. This is our polynomial functions, right? X squared, x to the third, x to the fourth, x to the fifth, and so on and so forth. Remember, there's a lot of sort of things that we know. If it's just x to the second, fourth, sixth, eighth, if it's an even power, they're both going to go up. Remember positive, even? Remember my end behavior dance? Those of you who had me? Yeah. Remember that? Positive, negative, right? Positive even, positive odd, negative odd. So this is positive leading coefficient, even, negative leading coefficient, even degree, positive leading coefficient, odd degree, negative leading coefficient, odd degree. So look, x to the fifth, positive odd, right? Positive, negative, positive odd. It's going to go up on the right, down on the left. So, and that pattern will continue. Odd powers, even powers, all of that stuff. Okay? And it will also have as many zeros as the power, all of those sorts of things that we learned, get out of there, way back when. Okay, now, if we have x to the fraction power, remember, x to a rational power is a root function, right? So if I have x to the 1/2 power, that's a square root of x. If I've got x to the 1/3 power, that's the cube root of x, okay? The function f of x is equal to x to the 1 over n is the nth root of x, right? For n equals 2, it's a square root, whose domain is 0 to infinity, and whose graph is the upper half of a parabola. Because remember, parabolas and square root functions are inverses of one another, so it's going to tie in really closely. For other even values of n, the graph of y is equal to nth root of x is very similar. So just like power functions where we have x to the second, x to the fourth, x to the sixth, if you have the second root of x, the fourth root of x, the sixth root of x, the eighth root of x, they're all going to look extremely similar. Same thing with odd numbers as well. However, if I take the third root of x, x can be any number, right? The domain of the third root of x is all real numbers because I can actually take the third root of a negative number as well. So while we only have the top half of a parabola, like we only have this, right? We only have that for the square root function. If I wanted the cube root function, we also have that because we can include negative x values, okay? We can have reciprocal functions, or what I would call them as inverse variations. Remember, when we put an x into the denominator, meaning we have x to the negative 1 power, right? A being negative 1 being power. If I have x to the negative 1 power, it puts it as 1 over x, which is that hyperbola with the two tails, where we have one happening in the first quadrant, one happening in the third quadrant. Its equation is y is equal to 1 over x, or xy is equal to 1. It's called a hyperbola with the coordinates and axes and asymptotes and all sorts of fun stuff. When we have rational functions, we have asymptotes. We could have slant asymptotes. We could have diagonal asymptotes. We could have vertical asymptotes, horizontal asymptotes, all sorts of fun stuff. This happens a lot in science equations where we have things happening inversely proportional to one another. Yeah, we'll talk about those a lot in real life application as well. And rational functions, I talked about them a little bit, but a rational function being 1 over x or any polynomial over another polynomial. So if I have two polynomials, p of x or q over x, this is considered a rational function. So like x squared plus 2 over x squared minus 2. That's a rational function. 2x to the fourth minus x squared plus 1 over x squared minus 4. That's a rational function. We have to always consider what x values are not part of our domain. Like we always have to say, okay, what's going on with the denominator? What can't x be? Like in this case, plus or minus 2. So you always have to be very careful of what's happening in the domain of this, because usually what's happening with the zeros in the denominator, vertical asymptotes, all sorts of things that we learned from the past 2 years. Okay. And then we have this thing that is kind of like a hodgepodge of stuff. It's like, okay, anything that's any other type of function that you could add or subtract other types of functions, we'll just call those algebraic functions, ones that you could add or subtract together. A function f is called an algebraic function if it can be constructed using algebraic operations, and taking roots, starting with polynomials. So if you have a mix of types of functions, and you're adding them and subtracting them or dividing them or whatever, you could call that an algebraic function. Okay. When we sketch these in chapter 4, we will see that their graphs can assume a variety of different shapes. We'll learn how to graph all of these different things. Okay, they look really funky. We're going to have some really funky looking graphs later on in the year. And then we have trigonometric functions. Trigonometric functions are sines, cosines, tangents, all those fun things that we learned about last year. Trigonometry and the trigonometric functions are, reference page 2 in your book. What was I going to talk about here? In calculus. When we use the function f of x is equal to sine of x, it is understood that sine x means the sine of the angle whose radian measures x. Thus, the graphs of sine and cosine are always shown like this. We are going to assume that we're talking about radian measured here. Whenever we use sine, cosine, we're not going to talk about degrees. We're just going to assume that we're always using radians, unless otherwise specified. Okay, and we've studied these graphs at length over the past couple years. Right. This is our sine graph. This is our cosine graph. Remember, it's cyclical. It goes in cycles. We have our periods, our amplitudes, our phase shifts, and things like that. Notice that for both the sine and cosine functions, the domain is all real numbers. it can go on forever left and right, but it will not go forever up and down, right? If you're looking at the sine, the range is -1 to +1, right? If you're looking at the cosine, again, -1 to +1. Those are the only outputs that I could possibly get. So while the domain is all real numbers, the range tends to change. And it will change based on the vertical stretch of the sine or cosine graph that you have. Okay? Just if I'm looking at my parent, though, sine and cosine, it ranges from -1 to +1 for the range values. Okay? Yeah, you could write them as absolute values as well. Remember that it is cyclical, so if I take +2 pi for any sine of an angle, sine of a radian, it's going to turn back out to sine of x. Same thing for cosine, right? If you add 2 pi to any angle measure, any radian angle measure, if you add 2 pi to any radian, it will come out to be the exact same thing. Sine of x plus 2 pi is equal to sine of x. Cosine of x plus 2 pi, because that's just making a full rotation along your unit circle, right? So any angle measure, if I add 2 pi to it, it's going to turn out to be the same thing. The periodic nature of these functions makes them very suitable for modeling repetitive phenomena such as tides, springs, sound waves, all sorts of things can be modeled with sine graphs. So let's take a look here. That was just kind of like a rundown of all the different types of functions that we could possibly have. So what we're going to do now is talk about some of those different types of functions and how their domains and stuff work. So what is the domain of the function f of x is equal to 1 over 1 minus 2 cosine x? What is the domain of this function? Now, it may look like there's multiple things happening here, and you'd be right to say that. I have two types of functions happening at the same time. So we would consider this like an algebraic one, because I see a trigonometric function happening in the denominator. And when there's x in the denominator, that's a rational function as well. So I have a rational function, and within the rational function, there is a trigonometric function. So it's almost like a composite, one inside the other. Now, let's first focus on the domain of cosine x. Is there any restriction on the domain of cosine x? Is there any restriction on the domain, the input of cosine? Like, is there any angle measures that I can't put in? No. Think about the cosine x graph. Will it go forever left and right? Yes. So therefore, there are no restrictions on the domain of cosine x. Now, is there any restriction ever for a rational function? Yes. What can't happen in a rational function? What can't happen in a rational function? The denominator cannot be 0. So here's what we say. The domain is all real numbers, but this has to be true, right? 1 minus 2 cosine x cannot be 0. If it comes out to be 0, that's no good. Okay? So all we have to do to figure out the domain of this entire thing is figure out what this equation solves to be. Let's do that. Got to get to my notes. Come on. All right, so first things first, I am going to, instead of subtracting the 1, I don't like negatives, so I'm going to add the 2 cosine x over to the other side. Man, I'm like an algebra teacher now. I'm showing all the inverse operations. Like, okay, we're going to cancel this. I'll draw a dotted line down the center. No. So we've got 1 is equal to 2 cosine x. We divide by 2 over to the other side to get cosine alone. So 1/2 is equal to cosine x. And then we take inverse cosine of 1/2 is x. Now, there's a lot of times where I'm going to ask you to not rely on your calculator, but rely on your knowledge of the unit circle. Okay? Like, for example, what angle measure? What's wrong?
Should it be not equal to 1?
Oh, I'm sorry. I always forget to do this. Okay. Sorry. Not equal to. All right. So now I need to figure out what angle gives me a cosine value of 1/2. What angle gives me a cosine value of 1/2? Anybody remember? Remember, is cosine x or y? Is cosine x or y? X. So I'm looking at what angle gives me a positive x value, right? So I know that it's within the first quadrant, right? It's got it, or first or fourth quadrant. because it's a positive x value. It's got to be on this side of the graph. So that means, and now let me ask you this, is there just one spot that gives that? No, there's two spots that gives this cosine value of 1/2, right? Okay. Remember the 45 family, the coordinates are radical 2/2. So which family is it in?
60.
So it's got to be either the 30 or the 60, right? Here's what I always do. Think about long side, short side. If we say 60 degrees, that comes out to be right there, correct? Okay, so draw on your little triangle. We know that's 1, right? The short side is the 1/2. The long side is the radical 3/2. Is that the x value? Yes. So we know it's the 60-degree family. So where does that turn out to be in terms of radians, though? So what is 60 degrees in terms of radians? Pi/3. Pi/3. Or, what's that one? 5 pi/3. Okay. Yeah, so it might be handy for you to go and find yourself a unit circle that you could print out and always have handy just when you're doing your homework and stuff. Trust me, I still get tripped up on a lot of this stuff. So I always cheat and have one right here. I haven't printed it off yet, so that was a little testing for me. But this is pi/3 and 5 pi/3. Now, my answers are pi/3 or 5 pi/3. And look, I'm going to leave a little room. Because are those the only possible answers? Plus 2 pi. Plus 2 pi n, right? Because n counting for all rotations that we could possibly have. We could keep going forever and ever and ever and ever. Oh, yeah. And remember, we're saying x is not equal to these things. I'm curious. What does this function look like? I really don't know. I didn't do this beforehand. 1 divided by 1 minus 2 cosine x. And I'm going to zoom 6 and see what happens. Weird. 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 For real? But that's weird. Okay, right. I don't know. See, there's weird. Sometimes these turn out to be really weird looking graphs. That's okay. I don't offend you. I'm really sorry. Graph of 1/1 minus 2 cosine x. All right, and then we have the tangent function. Remember that the tangent function is very similar. Not very similar. It's related to the sines and cosines. Remember, tangent looks a little different. Remember, tangent is sine over cosine. Y/x.
Sorry to be interrupted. At this time, we would like the classes of 7th grade teachers, Ms. Geddes, Mr. Tadinger, Mr. Kell, Ms. Jones, and Ms. Man, please go to the pod to have your photo taken. 7th graders that have teachers.
Oh, we
Geddes,
heard you.
Mr.
Sorry.
Tadinger,
She's
Mr.
like the
Kell,
nicest lady in the world.
Mrs. Jones, and Mr. Wortman, please go to the pod at this time. Thank you.
You're welcome. Now, think about tangent of x. You know, we know tangent of x is going to look like this generally, right? Then why does it have those vertical asymptotes all along the way? Well, remember that it has those vertical asymptotes because that's where cosine x is equal to 0. Think about what angle measure gives you an x value of 0? Well, it's from 0 up to 90, right there, at 90 and 270, right? Or in other words, at pi/2 at 3 pi/2. So that's why there's those asymptotes in there in tangent. Because I have all of those places, these places are where cosine gets us a 0. Okay, the x value is 0. So that's why it's going to be undefined there. Those vertical asymptotes there. And our last one that we'll talk about, maybe last. Nope, sorry, I lied. Second to last one we'll talk about is exponential functions. I I get to teach this Algebra 1 this year. We've never really taught exponential functions that much, but it is in the new curriculum. So we teach my Algebra 1 students exponential functions, ones with an exponential growth or an exponential decay. Basically, mathematically, all it is putting the exponent within the variable within the exponent. So y is equal to 2 to the x is exponential growth. Y is equal to 0.5 to the x, exponential decay. Remember, the domain is always all real numbers for exponential functions. It doesn't matter what I plug in, but I cannot get a negative back out again. Okay, I cannot get a negative back out again. So y is equal to 2 to the x that has an infinite domain, all real numbers domain, but the range is 0 to infinity. Same thing with 0.5 to the x as well. Exponential functions will be studied in detail in section 1.4. We will see that they are useful in modeling many natural phenomena: population growth, population decay, radioactive growth, radioactive. And then we have our inverse of exponentials, which is the logarithmic functions. Okay, the logarithmic function f of x is equal to log base v of x, where the base v is a positive constant, are the inverse of the exponentials. We'll take a look more in depth at section 1.5. This is the graph. I thought this graph was kind of cool because it shows you what happens if you change the base. Looking at those different colors, those are just changing the base. And it's actually decreasing the value of the base as we go up. Like this bottom one is log base 10. This one is log base 5. This one is log base 3. This one is log base 2. So as I gradually decrease the base, the line gets a little bit more shallow as it curves. Okay. Yeah, and we're assuming that we have a positive number down there. Assuming it's a positive number. Now think about it. Remember that the exponential functions have the domain as all real numbers and the range as only positives. Since the logarithmic ones are the inverses, that means now that's got to flip as well. So the domain is now only positives and the range is infinite, is all real numbers. So just be careful of that. Remember that if they're inverses, the domains and ranges will flip like that. Our last example of the day here is just classifying the different types of functions. It's pretty simple. You just have some homework problems on it, so I thought it would be good to give an example. Like for example, part A here is f of x is equal to 5 to the x. That would be an exponential function, right? Remember, whenever the variable is up within the exponent, that is exponential. B, when the variable is down in the base, that's a power function. You could also call this a polynomial. Okay, this is a power. I would be fine if you call it a polynomial as well, because a monomial is still a polynomial. Now, C, this is that funky one where we've got a couple different things going on. I see a rational function, but within the rational function, there's also a square root. So I would call this algebraic. Okay. I would call that algebraic. If you called it rational, I guess that would be fine too. But because there's a square root sitting in the denominator, it's got two of them working with it. So I would call this algebraic. And then we would call this one, that's an O. Oops, that's a P and an O. Polynomial. Polynomial. It's a fourth degree trinomial, right? Fourth degree trinomial. It's a positive if the leading coefficient was attached to the highest degree. It's a positive even, so I know the end behavior, because my end behavior dance. Positive even would go up on the left and up on the right. Again, these introductory sections are a lot of like different stuff happening at the same time. I hope we understand the general thing about this. The general pattern in this section was just that talking about all different type of functions that we could have and all the different ways we could make those functions. We could perform regressions on all these other types of functions that we have. And actually, your calculator does a lot of them. If you go to Stat Calc, you not only see linear regressions and quadratic regressions, but you also see cubic regressions, quartic regressions. There's another linear regression. This is a natural log regression, which is a log base E. We also have exponential regressions, f5 to the x, exponential regressions. We have power regressions, which is just a single, no polynomial type like that. There's also a logistic regression, There's sine regression, and then we would never touch manual fit. But there's all these different types of regression that you could do in your calculator. So you have not only the data side of it, but you also have like, okay, given pieces of information, like given 2 points, make the line, that type of deal. Given specific things algebraically, can you figure out what the equation would look like? All right, I'll shut up now. That's all I've got for section 1, 2. Let me stop the video.